In the last video, we started to look at the hydrogen atom, and what we ended up accomplishing is we were able to come up with the Hamiltonian in terms of center of mass and relative coordinates, and that ended up just being the total momentum squared divided by two times the total mass plus the relative momentum squared over two times an effective mass plus the potential, which only depended on essentially the relative position of our nucleus and our electron, basically the proton and neutron. And what we saw was this was sort of separable into Hamiltonian that only depends on the relative coordinates, and one that only depends on the center of mass coordinates, right? So we essentially have our Hamiltonian for our atom in terms separated into two Hamiltonians, one for the center of mass and one for those relative motions. And we also looked at how these operators behave, and essentially the total momentum operator was just the sum of the individual particle momentum operators, which in position space representation ended up being negative I h bar, the gradient of those relative center of mass coordinates, where the relative momentum operator was equal to m1 times the p2 operator minus m2 times the p1 operator over m1 plus m2, or in position space, this became negative I h bar, the gradient of those relative coordinates. Um, so that's sort of where we left off, and knowing all this, we're now in a position to start trying to solve this system. And by that I mean essentially what we're looking to do is solve our energy eigenfunction, where um, energy eigen equation, where we have some energy of the system, the Hamiltonian of the system acting on some energy eigenstate, I'm just calling it psi now, is equal to the energy of that system times that psi. So the main sort of technique that we're going to attack this repeatedly over the next few videos and in our next few discussions is separation of variables. What that boils down to is, if we were to write this in the position representation, we have our Hamiltonian acting on our system wave function is going to give us, where that's our full system Hamiltonian, is going to give us the energy of our system times that same wave function. We expect that that system wave function is going to be separable into the product of two wave functions, one that only depends on that center of mass uh, coordinate, and the other one, the relative wave function that only depends on that. Now, if we plug this sort of separated this wave function back into our energy eigenvalue equation, and follow sort of the process of separation of variables. Appendix E in the textbook actually goes over this quite well, and it's going to be part of a homework assignment, you showing this. But you end up with these sort of two different equations: the center of mass Hamiltonian, again just explicitly only a function of that center of mass variable, operating on the center of mass part of the wave function, ends up equaling the energy of that center of mass part times the center of mass wave function. So again, we get an eigenvalue equation for the center of mass part and another one for the relative Hamiltonian as well, uh, where it looks like this. And again, we're going to discuss this. We can discuss this more in our synchronous sessions, and it's also going to be part of the next homework assignment. The total system energy ends up just being the sum of those two energies, the center of mass energy plus the energy of that relative, um, the equation number 2 here. Uh, Now, if we look closer at this, we know if we look at equation 1 here, we know that our Hamiltonian of the center of mass is just that momentum operator squared over 2 times the total mass of that system. Um, we've solved this before. This is just a free particle, right? We solved this last semester in 323 or whenever you took that. Um, so this, if we want to write this in the position representation, it's negative I h bar del r, that operator squared times that wave function is going to be equal to E center of mass times that wave function. Uh, when we do this, we know, we can get, let me give us some more room here. We solve that wave function is just going to be one, it's 3-dimensional now, so this term is going to be cubed, but h bar to the 3/2 instead of just 1/2 times e to the I px times x plus py times y plus pz times z. We just get this sort of plane wave solution, and everything we did with respect to free particles still holds. We have the 1 over 2m times px squared plus py squared plus pz squared. So having, essentially this first equation just being a free particle equation, we can think back to our wave function here, and what do we have? Well, this, psi r times psi relative is just going to be this wave function, this 1 over 2 pi h bar to the 3/2 times e to that exponent there, times whatever our relative wave function is. This center of mass thing, this is essentially just a global phase. It's got this normalization constant out front too, but that's a global phase. That's not going to, if we think of sort of the subspace or let's say measurements that only involve the relative coordinate. So if you think of like a spectroscopy, a standard spectroscopy measurement where you're looking at the hydrogen atom and how it goes through say an energy transition from an excited state to a lower state, that's only going to involve the relative positions of the electron and the proton or the nucleus. That's not going to be affected at all by this whatchamacallit, this center of mass wave function, right? It's essentially a global phase. So when we're looking at measurements like that, our real focus is just solving that relative Hamiltonian. So this equation 2 up here that we got from our first round of separation of variables here, and that's going to be essentially the focus of the rest of our discussion on the hydrogen atom for this course is, can we solve this Hamiltonian that's just dependent on the relative positions of the proton for hydrogen, but the nucleus and that electron in the orbit, right? And again, we're going to use the same technique of separation of variables to solve for that. So let's do that, right? So we're trying, our goal now is to solve the energy eigenvalue equation for this, which in the position representation is just going to be negative h bar squared over 2 times that effective mass, the gradient with respect to those relative coordinates squared, plus the potential, which depends only on that relative coordinate, times or operating on our sort of what we've been calling our relative wave function, which only depends on r. That's going to equal the energy of this relative part of our system times that wave function again. Now, one thing we want to notice here is this potential, its essential potential, it doesn't really depend on the vector r so much as just r. right? That R coordinate, the distance between the nucleus or the proton and the electron in hydrogen. So this means it's spherically symmetric, right? So we want to use spherical coordinate system to solve this problem. So just a little bit of a reminder of our spherical coordinate system. If we're looking at our general coordinates x, y, and z, and we have, some vector r here that's, if we were to project down onto that plane is there. Our spherical coordinates are, let me do these in red. There's the polar coordinate theta, the azimuthal angle phi. Those are polar coordinate from the z-axis, positive z-axis down towards that vector. The azimuthal angle phi from the positive x-axis to wherever that vector is. And then r, the component in the direction of that vector, right? Just using sort of standard trig, we have the relations, our x component is equal to r sine theta cosine phi, right? R sine theta gives us this opposite side of that triangle, or this side, and then consider that the hypotenuse of this triangle, right triangle here. If we want that x component, it is cosine theta times the hypotenuse, which is r cosine theta, or r sine phi. Similarly with y, we get r sine phi times, or sine theta times sine phi, and then our z component is just r cosine theta. So hopefully we've all seen that before. If we want to consider, because we're going to have to at some point, a volume element here, right? So let's just take a differential volume element there. That dv is equal to dr times r d theta times r sine theta d phi, right? Or if we were to collect a bunch of terms, r squared sine theta dr d theta d phi. The way I like to think about this is think of a cube where the sides are in the directions of the unit vectors of your coordinate system, right? So we have a side of a cube that has length dr in the direction of the r hat direction in this theta hat, in the theta hat direction. We have a side of the cube that way. Since we're at some distance r, and d theta is just that angle there, the length of this side is going to be r d theta. So that's this term here. And then finally, a length of the side in sort of this phi hat direction. Well, it's going to be this distance times that d theta. So this would be the one going into the page here. That distance is r sine theta. So multiplied by that, sorry, d phi, not d theta. Multiplied by that d phi gives us the length of that side. So that's the volume element in our spherical coordinates. The Laplacian operator, if you look back at our Hamiltonian here, this del squared in spherical coordinates ends up being 1 over r squared partial, sorry, partial with respect to r times r squared partial with respect to r, plus 1 over r squared sine theta d partial theta sine theta d partial theta. Sorry, I'm running out of room here. Plus 1 over r sine theta partial phi Um, so that's our Laplacian in spherical components. So using these sort of identities and that we can now set up our differential equation we get from our energy eigenvalue equation in spherical coordinates. But before we do that, just quickly looking at this, I've forgotten to square everything on this last term in the Laplacian. But yeah, so yeah, with those squares, we have the Laplacian. Plugging that into our Hamiltonian, we get the Hamiltonian, the energy eigenvalue equation for our system as being negative h bar squared over 2 times that effective mass, all times. As fun as it is to watch me write this equation, we'll speed it up a bit. So this ends up being our energy eigenvalue equation. And remember, our goal is to solve for this wave function, which is a function of r, theta, and phi, and these energy eigenvalues as well, given our spherically symmetric central potential. The way we're going to go about this is just like we did in the previous part where we got the center of mass and the relative coordinates. We're going to look at this relative wave function, and we're going to use separation of variables and realize that this wave function that's a function of r, theta, and phi can be written as a wave function. Well, let's not use psi anymore. There's going to be a function that is only a function of the radial component and a function that we're going to call spherical harmonics later on that is only a function of those angular components. And then after we look at that, we're going to realize that this spherical harmonics can be split further, and we're going to end up with essentially a wave function that's composed of 3 parts: a radial term, a polar angle term that's only dependent on theta, and an azimuthal function that's only dependent on that azimuthal angle, phi. And we're going to essentially deal with each of these individually, following separation of variables, and then put them all together to get our full wave functions for the hydrogen atom. With that sort of outline of how our goal is to separate our wave function into these parts, we kind of have a path forward that we're going to use to solve this differential equation. We're going to start that next video lecture, and what we're going to do is actually going to review a bit about angular momentum, both classical and quantum, because there's a lot of parallels, and that it actually comes into this, and it'll kind of make clear how this separation of variables works. So again, we're going to do that. If you have any questions, email me. I'll bring them up in the synchronous sessions, and we'll get through this. I'll see you then.